Okay, good morning, everyone. So I'm really happy to finally meet you all, even if I met you the first day, but to get to know you better. So I'm going to teach the first half of the course, and then Aggie there in the back is going to teach the second half. And for today, we even have a guest speaker, so Rob Spekkens. So Rob is a faculty here at PI in the Quantum Foundation group. And I really think he's the best person to tell you why quantum theory is important. So I let Rob start. Thanks.
Okay. Okay. Can you hear me? Yeah, good. Okay. Morning. That's strange. Yeah, so Aggie and Maite asked me to say a little bit about quantum theory. Just see if I can get these slides working again. Okay, so what I thought I'd do is try to tell you, I'm the warm-up act. I have to convince you to pay attention carefully in the quantum theory course. Maybe you're already motivated to pay attention, but I'll try to give you a bit of perspective on the status of quantum theory today and research in quantum theory. So I thought it'd be fun to start off just by doing a bit of a comparison of quantum theory and general relativity. And general relativity is great, but the idea here, and it's a bit of a joke, is that quantum theory is better than general relativity. So or I should say, more important. Right? That's kind of where I'm going to go. So if you ask what are the pre-existing phenomena that people knew about prior to the invention of general relativity, which general relativity explained, the answer is there was the perihelion shift of Mercury. That was this one piece of experimental evidence that could not be explained with Newtonian mechanics, but which general relativity was used to explain. If you look at a similar list for quantum theory, it's much longer. You hear about a bunch of phenomena that, like the black body spectrum, discrete emission lines in spectroscopy, photoelectric effect, and even radioactivity somewhat. These were the phenomena that kind of motivated the people who invented quantum mechanics to do what they did. But if you ask what phenomena were known prior to the invention of quantum theory, which ultimately were discovered to be explained by quantum theory, the list is very long. So things like the periodic table of elements, the existence of isotopes, molecules, chemical bonding, the reaction rates in chemical reactions. So basically all of chemistry, all of condensed matter physics, like crystallography, the existence of different phases of matter, electrical, thermal, optical properties of matter, all of that required quantum theory for a proper explanation. Things like the facts that stars shine is explained by fusion, which requires quantum theory. The fact that there are elements at all, which requires an explanation in terms of nucleosynthesis, which is in terms of quantum theory, and on and on and on. So the things that were known in science, which ultimately came to be explained by quantum theory, is pretty lots. A lot of science, a lot of questions were ultimately answered by quantum theory. And then if you look at phenomena that were discovered subsequent to the discovery of these theories, well, there's things like for GR, the deflection of light by the sun is the famous example. Also the gravitational redshift of light. These days there's frame dragging effects, which people have measured experimentally. Also gravitational lensing on galactic scales now requires general relativity for explanation. And of course, in the last couple of years, we have gravitational waves, which clearly require general relativity. And presumably, there's some that I've left off the list. And then if you look at a comparable list for quantum theory, I haven't bothered because, open any journal in physics from any year between the early 20th century and now, and most of it, most of the new stuff is all requiring quantum theory to be explained. All right, so there have been some discoveries that were innovations to classical physics, since the early 20th century. But most of modern physics is ultimately about quantum theory. It's the theory that really does the most work in explaining the phenomena around us. And then finally, let me mention technological applications. So you might have heard that the global positioning system really requires general relativity to be accurate. That's true. And there may be other technological applications that of general relativity that I'm not familiar with, like perhaps very high precision clocks, I would guess, require general relativity to be properly explained. But if you look at, again, at a comparable list for quantum theory, it's very long. So maybe most prominent would be the understanding of semiconductor physics that led to the invention of the transistor, which now underpins the whole digital economy. The laser, nuclear power, medical imaging technologies like NMR, scanning tunneling microscopes, various material science things like metal alloys, semiconductors, superconductors, polymers, biomaterials, LCD displays, metrology, so the standards for the kilogram and the second and all those things are all require quantum theory. Applications in chemistry, biology, and then maybe a couple of more modern examples. So the squeezing that's required to get precision in the LIGO detectors for the gravitational wave detection involves quantum theory. And these days we have quantum cryptography, and we're trying to develop quantum computation. And the list goes on. The bottom line is an understanding of quantum theory is critical if you want to push forward the frontiers of modern physics. Most fields of modern physics require it. And if you want to develop new technological applications, then you should understand quantum theory. So probably you are all persuaded of this already. It's not really news that quantum theory is important. But I just kind of wanted to underlie, maybe, if you study it in the abstract, you might sort of lose sight of the fact that it really sort of underlies the modern world. Like, I don't think you can go around your life without interacting with objects that wouldn't be here were it not for quantum theory. So I think most of our modern life would have been extremely different. The world would be completely different if it were not for quantum theory. Whereas I think if it were not for general relativity, life could be similar. So anyways, that's the first point I wanted to make. Now, the second point is that in an undergrad education, one gets the feeling that maybe quantum theory is this sort of fixed thing that hasn't changed at all, and it was invented in the 1920s, and now we just use it. But I want to try to persuade you that quantum theory itself is evolving and has been evolving. And so, in other words, the quantum revolution that started in the early 20th century is still happening today. It's not settled. So in particular, there's a lot of disagreement about what quantum theory even means, which people in my field, the foundations of quantum theory, talk a lot about. But today I just want to talk about things like the formalism of quantum theory and the sorts of problems that people are applying quantum theory to. So let me remind you about sort of what you might consider the standard formalism. So the stuff you see in the textbooks are usually the Schrödinger or Heisenberg picture, which is this standard representation of quantum theory in terms of complex matrices or complex wave functions evolving via unitaries. So that's really the standard picture. Now, you might have seen the path integral representation of quantum theory before. If not, you're going to see it in Maite's part of this course. And then less prominent, but also sort of pretty standard, would be things like representations of quantum states and dynamics in terms of real valued vectors. So not complex matrices, but vectors of real numbers. And so if you've ever seen the block sphere representation, which is very popular in quantum information theory, that's an example of this kind of representation. And then there are particular examples of these representations where those real valued vectors have a lot of similar features to probability distributions. So for example, the sum of those real values is 1, and measurements are represented by vectors that kind of feel like they would be conditional probabilities, were it not for the fact that they have real values rather than values between 0 and 1, which is what you would require for a probability. So these are sometimes called quasi-probability representations, and an example of this is the Wigner representation, which people use in the field of quantum optics. Good. So I'm not sure, Aggie, there's going to be block spheres probably, but
yeah, block spheres, but we won't do Wigner function.
Okay, so you probably you'll have to wait to, if you want to hear about Wigner representation of quantum theory, you might have to wait to other courses on quantum theory that'll coming later. Perhaps the Foundations of Quantum Mechanics course will have that in there. But these are pretty old now, and they're you'll come across them in the textbooks of various fields. Now, first of all, these things are also not stagnant. I mean, there's insight into these sorts of approaches to quantum theory that continue today. So to give you just one example, in the field of quantum computation, where people want to analyze a quantum circuit. So this is like a classical circuit, but you start out by preparing things in quantum states and you apply gates to them. People have talked about different ways of trying to understand where the power of quantum computation comes from. And so these different formalisms you can take can give you different insight. So for example, if you do a path integral type of analysis of how to compute the overall action of such a circuit, you find that to solve for the action involves a particular problem in algebraic geometry that's known to be hard. There's a very different perspective if you take a path integral perspective than if you take the standard Schrodinger perspective. Or if you take this Wigner representation approach, you can think about a quantum computation as being akin to a probabilistic classical computation, where you get to sample your answer from a probability distribution at the end. So the Wigner representation, because it's so close to a probabilistic representation, it lends itself to a very easy comparison with that kind of approach to thinking about computational power. So these sorts of investigations have led us to, for example, generalize the notion of a Wigner representation to systems that have finite dimensionality, like qubits, two-level quantum systems. That's something that only came up in the last 15, 20 years or so, and was not there in the original proposals about the Wigner representation. So even the standard framework is progressing, but there are also, I would say, new approaches and also problems. So you might also get the impression from your undergraduate courses that if I just want to apply quantum theory somewhere, well, I just take the standard approach, apply it. There's no problems. There's no sense in which there's any ambiguity as to how to apply quantum theory. Well, that's not quite the case. So here's a list of some examples where I would say there is real controversy about how you ought to apply quantum theory. So the most obvious case would be gravitational phenomena. So we don't know how to quantize gravity. Different schools, different approaches take different attitudes on how you ought to do that. So some will take a path integral approach. Others will think about what the fundamental degrees of freedom are and quantize those. Still others don't treat gravitational degrees of freedom as fundamental. So it's not obvious in all cases how you ought to apply quantum theory. And in addition to that example, there's lots of others. So if you look at the second item on the list, there's a debate about actually what quantum theory says about superselection rules. So there's an idea that certain kinds of degrees of freedom cannot go into superposition. So if I have, for example, charge. So there's an idea out there that you cannot have a coherent superposition of different charge states. That's not allowed. Okay, so you might have thought if quantum theory applies, I can just write down a Hilbert space and have not only some discrete charge, but also superpositions of them. But there's some arguments as to why that should not occur. There's some counter arguments. People think that that's not right, that we should have superpositions of charge. People have the same argument over whether we can have superpositions of fermionic and bosonic degrees of freedom. And the argument has repeated itself in history many times. So in the context of superconductivity, people worried about whether the standard wave function for describing Cooper pairs, which involved a superposition of many different numbers of pairs, was actually valid or not, whether those superpositions really exist. And it was the same thing in the context of Bose-Einstein condensation, where people wrote down superpositions of numbers of particles. And this difference really had an impact on the kinds of questions people asked and how they proceeded. Some more modern examples. So people these days, the third item on the list, think a lot about whether it's possible to have superpositions of different spatiotemporal structures or different or causal structures. So could I have A before B in time coherently superposed with B before A? That's something that the standard quantum formalism doesn't really tell you how to address. And so people have to innovate on the formalism to try to address these questions, and there's disagreement about how to do it. Models of computation. So I mentioned a bit about that, but if I take a more esoteric models of computation, like cellular automata, it's not obvious, what a quantum cellular automata ought to be. It's not obvious how to make comparisons between classical models of computation and quantum models of computation. So something I'm interested in is this a new branch of statistics and machine learning called causal inference. And it's not clear, and there's debate about how to generalize that to the quantum sphere. Maybe I'll have time to say a bit about that. Also, if you've ever heard of something called algorithmic information theory, which has this notion of Kolmogorov complexity. Many people have tried to come up with a notion of quantum Kolmogorov complexity. There's lots of proposals. It's not clear how to do it. And then, more generally, there's all kinds of ideas in machine learning, and people are now trying to come up with quantum machine learning. But again, it's not unambiguous how you ought to do that. Okay, so an attitude I like to take on all of this is to say that in addition to the revolutions we're familiar with, which sort of take a pre-existing theory and replace it with something new and more empirically adequate than former, there's something that happens in physics which is more, it's a slow revolution. It doesn't change the physical theory. It doesn't overthrow the physical theory that came before it, but it changes your perspective on it, and it gives you a new way of thinking about it. So you can think about the use of action principles in the 18th and 19th century. It didn't overthrow Newtonian mechanics, but it definitely broadened the scope of things that Newtonian mechanics could apply to, and it gave us new insight into what Newtonian mechanics was really saying. Similarly with symmetry principles, these days we sort of bake symmetry principles into our theories by imposing them at the start. But there was a time when people sort of discovered the symmetries of their theories, like the Lorentz symmetry that was there in the Maxwell equation. So there's been a shift in how people think about the role of symmetry in theories. And I would say thermodynamic principles as well have played an important role. They're there at the foundations, at the birth of quantum theory as well. So all of these give you a kind of new perspective on pre-existing theories. An example that's especially relevant today, would be use of information theory. So if you come to a pre-existing theory and you look at it through the lens of action principles or thermodynamic principles or information theory or this thing called causal inference, it will lead you to formulate that theory slightly differently. It will lead you to different questions about what the theory implies, and it will really expand what we know about that theory. It will not just be answering questions from the perspective of the theory, but it'll be improving the theory and expanding the theory. So we've seen a lot of that with the advent of quantum information theory. Our understanding of quantum mechanics has really improved since the advent of quantum information theory. Good. So on that note, one of the innovations that's happened and has only recently started making it into the textbooks, perhaps it wasn't in the textbook you saw, was this change from the standard framework, which described vectors in Hilbert space, Hermitian operators describing measurements, unitaries describing dynamics, and measurement updates, how the state updates under measurement described by the projection postulate. Turns out that there's more general versions of all that. So the most general version of a state preparation is a positive operator that has trace 1, a density operator. The most general measurement is represented by something called a positive operator valued measure. And general dynamics, including open system dynamics, are represented by these completely positive trace preserving maps. You will likely see some of these in Aggie's version of the course, perhaps all of them. And also in the course on quantum foundations and possibly also the course on quantum information. And then finally, with the projection postulate, you have, again, not just projective measurements, but more general things. Good. So, Maite, am I right in thinking we've got about 10 minutes left in this little? Remember that clock is correct, yes? So at 25 minutes left. Oh, because we started at 10:45. That's right. Okay, 25. Good. Good. All right. Well, let me take a bit of time to give you some flavor for this. As I say, you're going to see it. So when I was a student, I remember prior to learning this stuff, there were sort of certain problems in the formalism as it had been taught to me. There were sort of clouds on the horizon, signs that there had to be something wrong. So I want to give you a couple examples of that, just to hopefully make it clear why we need these kinds of innovations. So let me consider how measurements work according to von Neumann. So von Neumann had this model of measurement where he said, if I have a system and some Hermitian operator A on that system, then I could write down a Hamiltonian that involved A, the operator I'm trying to measure on the system, tensor with the momentum operator on some probe system, which is going to act like a readout for the measurement. Some coupling constant. I interact them for some time, and then I do a measurement of the position of this probe system, and it will have been shifted by an amount that depends on the expectation value of A for the quantum state of the system. So this allows me to read out what the value of the operator A was on the system. So you can show that that is a way of measuring A. Now, if I have a second probe, and I do the same thing but with another operator B, then that's a measurement of B. And then the obvious question is, what if I do both things simultaneously? What if I couple my system using the Hermitian operators A and B that fail to commute to two different probes, and I measure the position of those two probes? The standard formalism says you can't measure A and B that don't commute simultaneously. So what could this possibly correspond to? It doesn't seem like there's any Hermitian operator that it could be measuring. And that's right. It turns out that when you work it out, what this corresponds to is a noisy joint measurement of A and B. So although you can't measure A and B perfectly jointly, you can measure noisy versions of them, and you need a positive operator valued measure to describe that. Okay, so a Hermitian operator does not describe this measurement. So it's just one example of how you kind of see that there has to be something more. Also, any noise in any measurement can't really be modeled by a Hermitian operator. It needs one of these POVMs. And so in some sense, the old formalism is this idealization that never applies to any realistic experiment. Every realistic experiment is slightly noisy. So there's a sense in which the old formalism is really an idealization that never occurs. Let me give you a second example, this one about the need to go beyond the projection postulate. So if any of you have done any quantum optics, you would have noticed the following, right? So this, if you read quantum optics books, there's photodetectors. And the way a photodetector works is that if I have a quantum state describing the electromagnetic field in some mode, and then my photodetector detects a photon, that's modeled by applying an annihilation operator to the quantum state. So if I think of these now as density operators, which you'll learn about, this is just the projector onto psi getting mapped to the projector sandwiched between A and A dagger. And that doesn't look like the quantum state being acted on by the projector. And that's what the projection postulate always looks like. It tells you, oh, you collapse into the eigenspace of the eigenvalue that you got. And this is a measurement that doesn't look anything like that. It turns out this is an example of a measurement update rule for which you need to go beyond the projection postulate that you'll be learning about. And so there's kind of if you read quantum optics textbooks and standard textbooks on quantum theory, there's sort of this mismatch in the nature of measurements. But if you supplement your standard textbook treatment with this modern treatment in terms of POVMs and completely positive maps, you have no tension any longer. Good. Okay, so the last little bit, I just want to give you a bit of a taste for maybe some of the research into quantum theory that happens here, but while still persuading you that the formalism of quantum theory continues to evolve. So I want to tell you a little bit about two more formalisms, two more frameworks that have been developed only recently, and that basically change the way we look at quantum theory, and I would say expand the range of applicability of quantum theory. They're a different way of formalizing the predictions of quantum theory, and they add to our understanding of it. So the first is something called the formalism or the framework of generalized probabilistic theories. So this is a framework that was introduced to really try to capture the purely operational predictions of quantum theory. So what I mean by that is the predictions of, if I do a certain preparation in the lab followed by a measurement, well, what are the statistics I'm going to see? Just that aspect of quantum theory. And so it was originally I mean, it has long roots, but in its modern form, it was first worked on by Lucian Hardy, who's faculty here, back in 2001. And then John Barrett, while he was a postdoc here in 2007, did some good work on it. And also these guys expanded that framework. And the first author here, Chiarbella, was also a postdoc at PI. So this has tight connections to perimeter. So I'm going to tell you a little bit about how that works. Very, very few details, but it'll just give you a flavor. So say you have an experiment like this one. You've got a preparation device over here with m different possibilities for the preparation. It spits out a system. The system goes into a measurement device. There's n different possibilities for what you're measuring. And then every measurement yields some outcome. And just for simplicity, we'll say it's a binary outcome. So the outcome's either 0 or 1. So these could be, for example, preparations of a spin-1/2 particle. These could be measurements of spin along various different axes, for example. So this would just correspond to spin up or spin down along that axis. But really, I don't need to assume any of that. It's just some arbitrary experiment. And the idea is that every physical theory is going to have to make predictions about what's going to happen in this sort of experiment. And I could always write those predictions down as a big matrix that tells me things like, what's the probability of getting outcome 0 if preparation 1 was done and measurement 2 was done? What's the probability of getting outcome 0 if preparation 1 was done and measurement 3 was done, and so on. Similarly, if I change the preparation to preparation 2 or preparation 3, I can just ask, what's the probability for all the different measurements? And notice that here I've just adopted this convention that measurement M1 always gives probabilities outcome 0. So I always assign probability 1 getting outcome 0 for measurement 1, just because that's a useful convention to adopt, kind of trivial measurement. So the point is that no matter what physical theory you have in mind, you can certainly write down what it predicts for the possible statistics you could see as you combine preparations and measurements together. And then the interesting observation is no matter what that matrix is, it always has some rank. So let's call its rank k. Then I can always factorize it into a matrix that is m by k times k by n. So m is the number of preparations, n is the number of measurements. And at worst, k could be the size of that original matrix. Maybe there's no compression. Maybe I need full rank. But in general, we find that k can be much smaller than the number of preparations and measurements you're doing. So in quantum theory, if we're doing that spin-1/2 particle, it turns out that that's a dimension 2 Hilbert space. The dimension of operators on that Hilbert space is dimension 4. And so this rank is k is equal to 4. I can always partition it using vectors that have these different dimensions. So now what you get is the following sort of representation. Every row of the first matrix represents a preparation, and every column of the second matrix represents a measurement. So I can think of the probability we saw of getting outcome 0 for preparation I and measurement j as just an inner product of the vector that represents the preparation I and the vector that represents the 0 outcome of measurement j. So these are now perfectly fine representations of those preparations and measurements. They allow us to compute the statistics we would see in this experiment. But what's nice about this framework is that it's completely general. It hasn't assumed that this experiment is described by quantum theory or classical theory or anything else. I can really describe any theory that predicts that I'll see, statistical, the relative frequencies of experiments will converge, for example. As long as it predicts that I'll see real statistics, I can model it this way. And so you can now start talking about the alternatives to quantum theory. So in the simplest case, where this rank turns out to be 4, if the world is quantum, then the set of states are a set of real valued vectors that live, because of the normalization, they don't live in the full 4-dimensional space. I can plot them in a 3-dimensional space, and they form a ball. So this is what's typically called the Bloch sphere, which you're going to hear about. The measurements live in a 4-dimensional space, which is kind of hard to represent. So I've just plotted 2 3-dimensional projections of them here. I like to call this the Bloch cone. It doesn't really matter exactly what it means, but it basically captures not just, for example, all the different spin measurements you could do, but also noisy versions of those. It's all captured here. So that's what quantum theory looks like in this formalism. But there are other physical theories, like these ones here, that basically make different predictions from quantum theory. So this is a famous one that's sometimes called box world. So it's what a qubit-like system looks like in box world. This theory was invented to prove that there are ways of violating Bell inequalities, which don't lead to superluminal signaling, but still aren't quantum theory, if that means anything to you. Anyways, this is a theory that I've worked on in the past, which is similar to a classical theory, but it says that you can't know everything. So it has these octahedral shapes here. This is a kind of randomly generated theory. And the point is that these are all things that you might go to the lab and find, that the world looks like this. One more comment on this, that you see these wireframes here. You can ask in any of these theories, not just what are the physically realizable states, like what are the things that I have preparations for, but also what are the logically possible states. So everything inside this wireframe cube is a state that would still give positive probabilities on all these measurements here in green. So they wouldn't generate negative numbers in the place where a probability should be. So in a sense, these are sort of conceivable states, but in this theory, they're not physically realized. And similarly with these wireframes, these are logically possible measurements in the sense that you would assign a positive probability to them for all these states, but they're not actually realized in this theory. Okay, that'll be important in a moment. So what's this framework good for? Well, the thing that it's mostly been used for is to try to articulate some principles that will pick out quantum theory in the landscape of all the ways the world could have been. So we now have this framework which can describe not just quantum theory, but classical theories and all these other alternatives to it. It's really unrestricted in what it can describe. And so what people do is they work in this framework and they say, this is the right arena in which to try to express principles that will allow me to derive the quantum case, right? So how can I derive the fact that for a two-level system, it's really this theory and not any of these other guys? What sorts of principles can get me there? So there's been a lot of work in quantum foundations in recent years coming up with sets of principles that get you to quantum theory. And so that's a real innovation, because previously we didn't have a good formalism for describing the landscape of possibilities. We had the quantum formalism, we had a formalism for describing classical theories. They looked extremely different, and we didn't have a very good common language. And now we do. A second thing that's relevant is that you can now use this framework to analyze your experimental data directly and look for possible deviations from the predictions of quantum theory. Because this framework doesn't presume quantum theory. You can analyze your data without presuming the formalism is the one that describes quantum theory. If you did that, you're already presuming that the world is quantum. This allows you to be agnostic about what theory describes the world and just analyze your data directly. So this is a project that I worked on with some people at the University of Waterloo. And I won't tell you much about the details. Let me just show you some data. So this is real data. This is a reconstruction for the polarization degree of freedom of a photon. So that's a two-level quantum system. If quantum theory is true, it should give you that block ball. But what we find is that the blue of physically realized states and the black wire mesh of logically possible states are not quite right on top of each other, as quantum theory predicts. So if you look back, you'll see that in the case of quantum theory, it said that all the logically possible states were physically realized. Those two things coincided. But in this experiment, because things are never perfect and things are slightly noisy, they didn't coincide. They were logically possible things that would have given positive probabilities on the measurements we did, the green places, that weren't actually realized in our experiment. But we can show that there's a sphere that fits between these two surfaces. So the data is consistent with quantum theory. Similarly over here, the quantum case fits between those two surfaces. We did it, if you ask what are the scope of possibilities for quantum theory being wrong, one way to measure that is the relative volume of those two shapes, which is about 91%. So maybe it's not a ball, maybe it's something different, but it can't be much different from a ball, because then those volume ratios would have to be larger. And in a follow-up experiment, we were able to do a much larger number of preparations and measurements, and we could get that volume ratio to about 97%. And then we could put other constraints on ways in which the world could deviate from quantum theory. But that gives you an idea for what this sort of framework is useful for. Okay, so then the final thing I'll tell you is one more framework, which asks questions about what quantum theory says about causal structure and cause and effect, what causes what. So this goes by the name of quantum causal models, and there's been a variety of work over the last 7-8 years trying to develop this framework, and it's still under development. It's not really in the final form yet. There's still some open questions and some work to be done. But again, I'm just going to try to give you a flavor for, and I'm going to try to persuade you that there's things that the old quantum formalism just doesn't do for you. There's questions that it doesn't answer. All right, so one of the things that you'll see if you take the course in quantum foundations is the Bell experiment. So this is a very famous experiment for the foundations of quantum theory. It assumes that you've prepared two particles together at some source, and you send one off to one region of space, and you measure it, and the other off to some other region, you measure it. And in the simplest version, there's multiple possible measurements you're doing here. So there's a knob setting, there's a variable s that varies over the settings here, and there's some outcome x, which I'll again assume is binary. Similarly over here, there's a setting t and outcome y. So you have four possibilities for which measurements you're doing. Both settings are 0, 0, 1, 1, 1, 0, or 1, 1. And you have four possible outcomes. You get outcome 0 on both sides, 0 and 1, 1 and 0, 1 and 1. And so when you run this experiment, so you repeat the preparation many times and work up relative frequencies of these different outcomes, you'll get some probabilities. So here, for example, for these settings, you find that almost like 43% of the time it's this, 43% of the time of that, and about 7% of the time it's this, and 7% of the time it's that. So that's an example of a prediction that you can get from quantum theory. So I can give you a quantum state of these two systems, which is entangled, and particular quantum spin measurements, for example, here and here, that give you exactly these statistics. And similarly for the other rows, I can find different choices of measurements for S is 0, S is 1, T is 0, and T is 1. That'll give exactly these kinds of statistics. And what Bell's theorem shows is that it is very hard to explain these statistics causally. So let me tell you a little bit about what that means. And I mean, I'm not going to go much into Bell's theorem in this talk, but I guess what I want to persuade you of is there's more to say than just this is what you should expect to see in the experiment. So if you have a very instrumentalist position on quantum theory, you might say, well, the purpose of a scientific theory is to just predict what you're going to see in an experiment, and once it's done that, it's done its job. There's nothing more to ask. So you might be happy. If you say, well, the formalism tells me what I should see in terms of relative frequencies, I'm happy. So I want to kind of suggest that that's not enough. So let me do that by telling you about a paradox of statistics called Simpson's paradox. It'll take a few minutes to describe. So you've got a population of people who have some medical condition, and you're testing out some drugs. So you keep track of who's taken the drug. And in the population of the people who've taken the drug, you find out how many of them recovered. And in the subpopulation who didn't take the drug, you figure out how many of them recovered. And you notice that the recovery rate is higher in the subpopulation who took the drug. And then you decide to look at just the men. And then you find it goes the other way. You find in the subpopulation of men who didn't take the drug, the recovery rate was higher than in the subpopulation of men who took the drug. And then the paradox comes when you notice that for the women, it's the same as the men. The recovery rate is higher among those who didn't take the drug. So for the men and the women individually, it looks like it's better to not take the drug, but overall it looks like it's better to take the drug. And that seems like a paradox because how do you decide whether you're supposed to take the drug or not based on that sort of data? And if you hadn't seen it before, this is just an example. You can find some other examples of this on Wikipedia if you want, of actual numbers of people, like 300 men took the drug and 180 recovered. Calculate the recovery rates for this data, and what you'll find is that for For the men, the recovery rate is bigger, and you don't take the drug. Similarly for the women. But if you take the totals, like here, the total of the people who took the drug is 400, the total who recovered is 200, you'll find it goes the other way, that for the combined statistics, higher recovery rate for those who took the drug. So the question is then, how do you resolve this paradox? In particular, how do you figure out what you should do if this is the data you have? And so the argument is that you can't just look at this data. You have to go beneath it and ask for a causal explanation. So here's what's going on causally. So first of all, here's why it seems like a paradox. So this is the causal explanation that people often have in mind. So you might think that the treatment could have a causal influence on recovery, and maybe gender also, in the sense that men and women could recover at different rates from this particular medical condition, irrespective of whether they got the drug or not. But if that is the causal structure, then there really is no way to see this kind of reversal we saw here. Because, for example, if that were the causal structure, you could compute the left-hand side here by just taking a weighted average of these two quantities with the probability of somebody being a man and the probability of somebody being a woman in that population. And so if you took the weighted average of these two equations, you would definitely get that the inequality went the other way. So that causal explanation can't possibly fit the data. And it turns out that's because this is the causal explanation, that the gender actually had a causal influence on treatment. So this particular population, gender actually determined people's likelihood to take the drug. So for whatever reason, men were more likely to take this drug than women were. So the idea of the positive correlation we saw, you can explain it, this correlation between taking the drug and recovering, as follows. For this medical condition, men are more likely to recover than women. Men are also more likely to take the drug than women were. And therefore, when you see that somebody has taken the drug and you ask, what do you think? Should you believe that they recovered or not? Then you ought to reason as follows. If they took the drug, they're more likely to have been a man. And if they're a man, they're more likely to have recovered. That's a positive correlation. You should update your beliefs and assign a higher likelihood to them recovering based on the evidence that they took the drug. But it doesn't mean that the drug's effective for recovery. In fact, in this experiment, it's not, right? Because when I look at just the men, so now there is no common cause of treatment and recovery, because I'm focusing in on that subpopulation, then I find that treatment is not effective for recovery. So the point is that correlations alone can arise from common causes or cause-effect relations. And just looking at the statistical data doesn't tell me which it is. I have to look deeper, and I have to look at the causal explanation of that data. Okay, so for the quantum experiment, what it means is that the standard quantum formalism doesn't answer the following sort of question. Should I think of the correlations that we see between these outcomes as being by virtue of the fact that what I choose to measure here has an influence on the properties of the particle over here? That's what this arrow means. And that's why this outcome over here comes to be correlated with X. Or is it just that there's a common cause acting on the two systems? And when I learn the value of the outcome here, I update my knowledge of the value of the outcome over here. And that's what the correlation describes. This is just like the drug either influencing recovery or there being a common cause like gender that correlates the drug and recovery. And my point is that just like in the drug trial, that data table didn't tell us what was going on. We had to do some further analysis. It's the same in quantum theory. The standard quantum formalism just doesn't answer questions like, is this what's going on causally, or is this what's going on causally? And Bell's theorem shows that if you take on board the idea that these quantum systems are described by some variable that just captures their properties, about which you might have some lack of information, then you're essentially forced to say that this is the causal structure. So this is where the term spooky action at a distance comes from, that you're forced to acknowledge that there's some causal inference from this wing of the experiment over to this wing here, even if I do them at space-like separation. Okay, so that's why quantum theory, Bell's theorem suggests that there's a kind of tension between quantum theory and relativity, and it has to do with trying to find causal explanations of the correlations we observe. So the new framework I was telling you about is an attempt to maintain peaceful coexistence with relativity by saying this is in fact the causal structure of this experiment, and to try to understand the innovation of quantum theory as being an innovation about how we describe our incomplete knowledge. So again, I can only give you sort of a taste for what this looks like. So let me just say that in this formalism, when we do this collapse rule in quantum theory, we say the quantum state of system B, when I learn that system A was measured with setting S and gave me outcome X, that updating of the quantum state that I do upon getting those outcomes should not be thought of as a physical influence from this measurement device across space to system B, but rather as a kind of Bayesian updating. I've learned something about system A, which has taught me something about system B. So classically, it would have just been an updating of the probability distribution over B that describes an agent's incomplete knowledge. So that's the kind of picture that you want if you're going to explain this in terms of just a common cause. And then you need a certain amount of formalism. So over here on the classical side, let's ask ourselves, what are we given and how do we compute this? So what we're given in a classical experiment like this would be a joint distribution over the variables A and B. That's this PAB. And we might be given a characterization of this measurement as the probability of any outcome X given the variable A and the setting variable S. So we have those are the givens. This is what we want to compute. So if you learn the basics of classical probability theory, what you find is the first step would be something like this. You say, well, what does learning X and S teach me about A? So I want to know A given SX. Oh, well, I have to do a Bayesian inversion on this quantity. So I take X given AS, multiply by the probability of A, divide by the probability of X given S. That's the formula for the thing I'm looking for. And then secondly, I might say, well, what does A teach me about B? Because I want to update my knowledge about B. Well, what I'm given is a joint distribution on A and B. Classical probability theory tells me to compute the conditional B given A just by dividing by the marginal probabilities on A. And then finally, I can compute what I learn about B given S and X, just in terms of what I learn about B from A and what I learn about A from S and X, and I sum over A. So this is just all a standard calculation in probability theory for how I ought to update my knowledge about B when I learn the values of these variables. So the idea of quantum causal models is to try to explain the remote quantum collapse in the same way. You're given some quantum state on AB. Think of it as what you know about systems A and B. You're given a characterization of the measurement over here. Think of it as, the measurement over there. What you know about X given S and A. And then you just need analogs of all those steps on the left-hand side. So that's what these formalisms do. They give you an analog of Bayesian inversion with a particular kind of operator product, which I won't specify exactly how you define it, but there's an operator product that acts like multiplications of probabilities. There's an inverse operation. And you have a way of computing conditionals and a way of propagating your knowledge using a trace type formula. And the point is that this is not what we would normally call the formalism of quantum theory. Like in particular, it involves these conditionals, which typically we don't talk about in the formalism. But it has interesting applications in the sense that if this can be made to work, then we can do a lot with it. We can decrease the tension between quantum theory and relativity. We can go beyond these Bell scenarios to other types of causal structures and ask, is there a discrepancy between what quantum theory predicts and what classical theories predict? Does quantum theory offer advantages for figuring out what the causal structure is when we just have statistical data? These are all just examples of the kinds of problems that people are developing quantum causal models to solve. So yeah, with that, I think I will finish up.
So any questions? So let's thank Rob again.
Yeah.
You have a question?
Yeah. When you factorize the probability matrix, you too, there's some freedom in the factorization. For example, you can have different scalings. So the first column fixes the norm. Is the role of the first column to fix the norm of the factorization? You fix the first column to 1. Right?
Yeah. Oh, thank you. Yes, I should keep using this. I mean, you could adopt other conventions, but that one is particularly useful, for example, for connecting to the block sphere representation, which we really wanted to do, so that our representation of the quantum case looked familiar. It looked like the block sphere representation. So it is connected to the normalization, but I would say our main motivation was just to make the quantum case look as familiar as possible.
But, given the first column, there's no freedom in the factorization.
Are you saying, does setting the first column to 1 imply something about the minimum rank, or what? Sorry.
Given some
Yep. Can you always make the first column 1? Is that? No. Yeah.
In general, if you
Yes.
have a matrix of rank k lower than the number of dimensions, then say you can factorize it like you did.
Yeah.
But there's some normalization or some freedom in your factorization, right?
Yes, there's in fact a whole linear freedom, right? So if I can always introduce a linear transformation and the inverse linear transformation. So let's call one the state matrix and the other the effect matrix or the measurement matrix. I can introduce a linear transformation of the measurement matrix and the inverse of that transformation acting from the right on the state, and I get exactly the same predictions. So in particular, like all those pictures I drew, you could distort them by a linear transformation, and they would be describing exactly the same theory. So I didn't go into that, but yeah, there's this freedom of representation, and we just conventionally represented one of those cases. Okay, well, if you have more questions about why bother studying quantum theory, you can come see me or talk to people in quantum information or quantum foundations groups.
Few minutes to introduce what is going to be this course. So before starting, it's a completely new course. Okay, so we are going to try many things. So don't hesitate to, and maybe some of them you're not going to like it, but so don't hesitate to give us feedback, okay? And possibly, if it's possible, constructive feedback is always appreciated. So yeah, so what is the idea of this course? Not much, okay? So let's try. Yeah, so quantum theory, as Rob just mentioned it, you can talk about many frameworks, okay? And really the idea of this course is to introduce you different frameworks, because as he already said, it's like with the example of this quantum circuit that he showed you, is that some calculation can be easy, one framework, and some calculation would be very difficult, and the same calculation will be very difficult in the same framework. So we want to introduce different frameworks because also depending on which field you're going to work doing your research, you will work rather in one or the other, okay? So let's start. I'm going to start with the canonical framework, and I will consider that this is a kind of standard framework. So in this framework, we're going to talk about Hilbert space, Hermitian operators, and I will consider that it's a kind of minimal background that you need to have to talk about quantum theory. And yeah, so we're going to start with that. And then I have chosen to introduce you some path integral formalism. So you will see that in quantum theory, none of the calculation we're going to do using path integral are going to be easier than with, for example, the canonical framework. But what is the motivation why I'm introducing this path integral is because then so you have 3 weeks of quantum theory, and then the next 3 weeks, you're going to jump into quantum field theory. And in quantum field theory, for some of the calculation you're going to do, you will really need the path integral formalism, and some of the things, some calculation you won't be able to do them without this formalism. Okay, so I really want to introduce you this path integral formalism, and it's a really big topic. So since I only have half of 3 weeks, which is like 7 lectures, I won't be able to present everything. So I have chosen to talk about perturbation theory because it's a way to introduce Feynman diagrams, and it's something that in quantum field theory, you're going to do calculation using Feynman expansion, okay? And it's, I think, useful to see it a first time in the context of quantum theory, which is a bit easier, okay? So I won't think I will have time to talk about Fermi path integral, where in the case of Fermi particle, you would need to introduce Grassmann number and anti-commuting numbers and this kind of thing. But it could be also something that is going to be really useful for quantum field theory. So depending on the pace I'm going, maybe I will say a few words on also Fermi path integral. Okay, then after that, I think I will be done. And Aggie is going to do the second half of the course. And within the canonical quantization framework, one problem you can have is talking about many body system. And in this case, usually then you will need to introduce a bit more general framework, which is called the second quantization. So this is what Aggie is going to talk about. And then as Rob tried to motivate, one very useful framework is the operational framework, where, as he mentioned it, in this context, you are going to consider kind of generalized axioms, sorry. And because you have generalized axioms, maybe you can consider situation a bit more general than in the other framework, okay? And again, Aggie is going to talk about that. So really this framework is kind of based on a kind of minimum set of axioms. And now, as you maybe have understood with Rob's presentation, the abstract elements now are going to refer to really experimental procedures, okay? So this is really the idea of this operational framework. So of course, so this is just a choice of some frameworks for quantum theory that are not always easy to connect between all of them, okay? Sometimes you can, for certain kind of problem, you can really go from one formalism to the other, but as I said, sometimes you can only do a calculation in a given framework, and it's not so easy to see the connection, okay? So what is then the idea? So the first framework on the top of this slide are going to be really useful for everything related to QFT. And so, for example, myself, I'm working in quantum gravity and in more or less in the loop quantum gravity framework. And the idea of loop quantum gravity is really to take seriously general relativity and try to apply the more or less canonical quantization framework to general relativity. Okay, so you see that even doing research, you're still more or less using some of these frameworks. And of course, we also have a kind of path integral formulation, which is called the spin foam approach, where we use a kind of path integral formulation. So this is also frameworks that are related to research area. And regarding the operational framework, you're going to, if you take the courses in quantum information in the second half of the year, where you can choose between the review and even exploration courses, you will have some quantum information course where you will use this operational framework. Then Aggie is working in quantum optics, and I think most of the examples she's going to use come from what she's doing in research, quantum optics. And this is also a framework that is really useful in this context. And as Rob mentioned it, working in foundation of quantum mechanics, you really have to think about what are the axioms, what are the most generalized axioms I can use to deal with any kind of experiments, okay? And so in foundation of quantum mechanics, if you take this course in the second half of the year, you will also use a lot this operational framework. So these are a bit the idea and the motivation of the course. To show different frameworks is to get you ready for these different courses, but also to do research in a way, okay? Okay, any question on that now? So now let's just make a short break. The first half of the course was really dense. So before jumping into the topic, I just want to say that, so of course we're going to do mainly only physics and a bit of math in this course, but we want also to take since it's the first course in core courses, and as you have seen already, the pace is accelerating. You have 1 hour and a half lecture twice a day, and you will have tutorial almost every afternoon. So you really need to think about, and of course, usually courses are going to be very dense, to think about time management, learning tools, and this kind of thing. And so in this, as I said, in this course, we're going to try many new things, which are not only about the content, but also the way we're going to present things, okay? And the way we're going to work in tutorials, the way we're going to give you homeworks. So maybe just about the homeworks, for example, so the first one, I'm going to come back on it in a moment, but for the next 2 homeworks, we're going to give you the homework a bit ahead of time compared to usually. So for each core courses, you will have 3 homeworks, and usually you have 1 week to do it, okay? So it's short and everything. So here we're going to give you a bit more time to do them because, for example, the second homework, you will receive it hopefully tomorrow, if I can finish it, but this is the idea. And then you will have until the end of next week, so you have 10 days, and it will be the same for the other homework. And one of the instructions will be, please, as soon as you receive it, read all the homework, because one idea is to learn efficiently. Usually, if you're trying to learn something linearly, meaning you just listen and you try to absorb everything, it's not always the most efficient. So sometimes it's more efficient if you read already your homework instruction. When you go to the lecture, you can maybe focus a bit on, you have some idea of what you need to understand and which way, and you can start with that and then expand your knowledge more in this way rather than to go linearly. Okay, so this is the kind of idea. Then we see that in tutorial, we are going to use a lot this peer-to-peer instruction, but I'm going to come back on that. So now I just want to talk about the homework one. So it's the first time we're doing that, so you may not like it. I know that. But what is the idea of this homework is that it's based on a continuous assessment. So every day, so you should all have received already an invitation to edit a Google document. If you haven't, please come to see me at the end of the class. And the idea is that at the end of each lecture or each tutorial, you will look at your Google document, and this document will have been updated, okay, with questions. And so the idea is that please answer the question the same evening or the morning before the lecture, if you have time, depending if you want to, if you're rather early bird or late one, I don't know. And then you will receive feedback from that, okay? So we have an amazing TA. You're going to have an amazing TA. Tomasz is not here yet, but you will see him this afternoon. And he's the one who is going to look at your homework. He's going to be there for your tutorials. And he's going to give you feedback every day on your question. So yeah, the question will be on the lecture and on the tutorial of the day. So what is the motivation and the advantages of this homework is that you're going to work regularly. So 3 weeks is really quick. You're going to get a lot of information. So you really need to get used to work regularly and also to take the time after one lecture to think about what you learned, what you did not understand. You don't have to understand everything from the first time. This is totally fine. But it's much more efficient if you're already aware that you haven't understood something, and then you can come back on it later, okay? And then you will get feedback regularly, and it's going to help you to make connection between the different lecture and tutorials. As I said, this course is about different frameworks that can sometimes seem disconnected. we will be able to do, Aggie and I, to do some of the connection, but not all of them, okay? So it's also up to you to work more, to think about what we have seen, to make some of the other connection, if it's possible, or to understand what is the difference, why you cannot use this framework in this context, or why you can use only this one, okay? So this kind of thing, you will have to do this part of the work also a bit by yourself. Any question about this homework? Is that clear? Okay, great. Tutorials. So again, tutorials are mandatory. And what I want to say is that at least once a week, even a bit more, the tutorial will start with a group activity. So the idea is that the group activity is to help you learn and to give you some kind of learning tools. So not everyone is going to learn the same way. So not everything is going to work for everyone. Okay, so we are going to try different things, and you may not like some of them, you may like some of them. So the way you learn really depends, of course, on your personality, but it's also something cultural. And you're here in North America, where most of the way you learn is by speaking, by talking, by presenting things to the other, okay? And I can tell you that it's something really important. So my daughter is 4, she's going to daycare, and already at this age, once a month, she has to bring something from home and to present it to her friends. So she's already training her presentation skills. So I'm sure that when she will be going to the university, she will be very confident, and it's going to be something very easy. But I know that it's not the case for everyone. I come from France, and in Europe, I would say that it's not so much the case. In Asia, for example, I would say that the way of learning is more introspective way. So it can be, I know that culturally you don't also do all the same things. So if you don't feel comfortable with one of the activity, you can let me know, of course. And usually you will always have an option to choose the way you interact with your peer. But what I want to say is that you're also all here to do research. And the way research is working, usually it's a collaborative way. And most of the time, first, you're going to be student. You cannot be faculty directly. So as a student, you will have to report things to your supervisor. And this means that you will have to explain idea to the supervisor. You will have to share calculation, explain what you have been doing. And usually, the most efficient, you can, of course, send documents, written documents with this, but usually at some point, you will have to explain orally, okay? So it's a good way to start working on trying to explain something difficult, even if not everything is completely clear to you, but it's also a way to try to understand better is by talking with someone, asking questions, and trying to answer, trying to explain, okay? So this is just what I wanted to mention, and tutorials are part of homework 1. So this means that some of the questions you will receive on your Google document will be coming from the tutorial to help you also, because sometimes you do a tutorial with many calculations, and at the end you're like, okay, I did this calculation, but why? What was the idea, the big picture of this tutorial? So you get a bit lost. Okay, so this is just regarding homework 1. Okay, so just quickly now to come back on the course, the outline. So as I said, I'm going to do the first half. So today it's the introduction, and I'm going to mention quickly, because I don't have so much time, which kind of mathematical prerequisites you need. And then tomorrow I will start with the Dirac quantization, which is also called canonical. And hopefully on Friday, I will start the path integral, okay? And introduce Feynman diagram at the end of of my time. And then Aggie is going to start on next Thursday with second quantization, and then this notion of generalized axioms, okay? Okay, so you already had a bit of that with Rob's presentation, but since you all did undergraduate, usually in an undergraduate course, you often start with a notion of a wave function, okay? So wave function is going to be evolving according to the Schrödinger equation. And of course, some problems can be solvable with this formalism. You can deal with the problem of a particle in a box, look at the harmonic oscillator, hydrogen atom. But this wave function, in fact, is not really physical in a way that it's not a square integrable function, so it's not part of the Hilbert space, if we define a Hilbert space as the space of square integrable function. So it's not so trivial, in fact. This formalism, we will have to really give a well mathematical definition of this framework. We, in fact, have to extend the notion of Hilbert space, or to work with maybe, so this is more Dirac's approach, where he's going to introduce the notion of rigged Hilbert space. But you could also work from the Feynman point of view, where you try to really keep the notion of Hilbert space and you define generalized operators, so which are going to become the POVM. And this is going to be what Aggie is going to talk about in the operational framework. But so just to say that, yeah, these are some limitations. And in fact, this wave function is really just a representation of an abstract vector, okay? And indeed, when you have an abstract vector, usually to do explicit calculation, you are going to represent that as you're going to represent that, so you choose a basis, okay? And for example, the wave function in terms of x is just when you, or r here, it's just when you choose the position basis. But really what is important here is, so this is what you should all be familiar with, and maybe some of you are already familiar with the more abstract formalism, which is, and or hopefully at the end of this course, everyone will be really used to this abstract formalism, where now what is really important is vector, and indeed with such vector, you can consider more general properties, such as the spin, the particle number. So for example, the spin is just a discrete internal degrees of freedom of a particle, and it has nothing to do with a wave motion, okay? So you really need something more than wave function to talk about the spin of a particle. And of course, so as I already mentioned, what is important is really the abstract structure. Why? It's because what you want to do in quantum mechanics is you want to do a prediction about a measurement. This prediction is a number, and in fact, this number is not going to depend, the number you're going to get is not going to depend on the basis you choose. So it's not going to depend on the representation. It's only going to depend on the abstract vector, and usually, so when you do a measurement, you measure a physical quantity, and at the quantum level, a physical quantity is an Hermitian operator. And again, so the number you give is depending only on the vector and this abstract operator, okay? It's not depending on the basis you're going to choose. So we really, the only thing that matters is really the abstract structure behind everything. And if you want to talk about vectors, the abstract structure is going to be vector space then. And even we are not going to be interested in any vector space. We're going to be interested in Hilbert space. I'm going to come back on the definition of a Hilbert space. Is just a complex, a specific case of a complex vector space, okay? And as it was already mentioned by Rob, in fact, even in this abstract setting, you cannot treat all cases, and you will see that here, when you talk about a vector, this means that you are considering what is called a pure state. And if you want to deal with what is called mixed states, then you really need to introduce this notion of density matrix, okay? So what is a density matrix? I'm not going to use it so much in what the example we are going to do, but you're going to use it a lot with Aggie. And in fact, everything we are doing using only vectors and operators acting on a Hilbert space could be formalized already with the notion of density matrix. So a density matrix is just a specific Hermitian operator that is positive, and usually you choose the normalization that the trace of this operator is equal to 1, which is equivalent to say that you choose a normalized vector here, okay? So this is a kind of condition you put on this. And of course, so this means that we need to deal with linear operator, but already here, if you have a vector, you want to act on this vector, and to act with this vector, you need an operator, okay? And something that is going to be really important is that, quantum mechanics is not deterministic, okay? It's going to predict only the probabilities of various alternative possible events, and so you really have to think about to know a bit about probability theory. So I'm not going to talk so much about it, but keep that in mind because the way you really interpret your result really have to be with that in mind. Okay. Okay, so this is the essential mathematical topics for quantum mechanics that you really need to know, be familiar with. And I guess hopefully you're already quite familiar about vector spaces and operators. So for today, since I only have 15 minutes, I'm just going to do a very quick overview about these first two topics. And then in the tutorial this afternoon, you will have a first kind of group activity where you're going to work on this. We'll have some problems related to this definition and try to do some proof and this kind of thing before going to the physics. Okay, so this is really the math that everyone needs to be familiar with to then deal with anything. So any question right now? Not yet, okay. So are you already really familiar with all this abstract notation or everyone is only familiar with wave function? No? And are you already familiar with the notion of density matrix? Okay, great. So it's going to be good, more easy. Okay, so I start with the basic and it's going to be just to make sure that everyone is on the same page. So first the definition of a vector space. So it's a set of elements that is closed under addition and multiplication. And this sentence exactly means that. This means you take two vectors. It's not me, okay. And then the sum of these two vectors is still an element of this vector space. Okay, so do you have examples of vector space? Very simple one. Yeah, the element of just an element of number or even Rn, and then you have a vector and dimensional vector, but also the space of, so the space of function is also a linear vector space, okay? So then what is really important is the inner product. So do you know what are the properties to get the inner product? Sorry?
Positive definite.
Yeah. Okay, so I'm going to, this is an important one. You also want, so the idea is that you take two vectors, it's an ordered pair, and then the result gives you a scalar, okay? Okay, so this, okay. So yeah, this gives you a complex number, then this tells you that it's linear in the second argument, so if you combine that with the second property, it gives you that it's anti-linear in the first argument, and then you have the positivity. So any examples? So if we go back to the first two examples that we had, of course, if it's only vector, then you all know that this gives you, defines the scalar product. And then if you take functions which are square integrable, then this integral here defines you the scalar product. So you should be all familiar with that. So I'm not going to spend too much time on that. And then something that is really important, and maybe you're not so familiar with that, is that if you have a linear vector space, you can define the notion of dual space, which is form of linear functional. Okay, and this linear functional is also, so it's linear. So this is exactly what I tell you. And one very important theorem that in fact you're using all the time is this Ritz theorem, which tells you that there is a one-to-one correspondence between linear function and vectors. And in fact, you're using that all the time because I guess you're all familiar with the Dirac's notation. So in Dirac's notation, a vector is then just a ket, a linear functional is just a bar, and then the evaluation of a function, the function on a vector gives you just a number, and this is that. But you can see that using the dagger of a ket, you get a kind of bar, so you have this one-to-one equivalence. Okay, here that appear very easily on this for this Ritz theorem. Okay, so now if we go to operator, so you have vector, so you want to act on this vector, so you're going to use an operator, and this gives you another, you act with an operator on a vector, this gives you another vector. And this operator is linear if you add this condition. And then, so do you have any example of a linear operator? Sorry?
Derivative.
Yeah. On function, you will have the derivative operator. And for example, on vector, you can just have a matrix. Okay? So the operator will be matrices. And on the function space, you will have differential or integral operators. So for example, here you're just acting with a matrix. So this is just a matrix product. And then for differential operator, you see that you can have this kind of equality. This equality has to be understood as an equality on differential on operators. So this really means that, of course, how do you understand that?
This when we act on a function.
Yeah, okay. So of course, if now you had the psi of x here, and you act on it, then you can understand this equality. So this has to be understood in this way. So this is the kind of equation you can have on operator, remembering that an operator is defined by its action on vectors. Okay. So we define, oh, there is a hay on his own here. We define the action to the left on ket vectors, but you can define also the action on the right to bra vector and define the notion of adjoint. Okay. So I'll let you read just the definition. And now something that is going to be really important in quantum theory is the notion of Hermitian operator or self-adjoint. So of course, Hermitian and self-adjoint operator are the same thing for finite dimensional operator, but as soon as you go to infinite dimensional, be careful with the distinction between the two. So let me give you the definition of self-adjoint. So it's just an operator that is equal to its adjoint, which means that you have this equality and the domain of A is the domain of A dagger. Okay? And of course, this is true. And Hermitian is only this part. Okay? So if in the case of finite dimensional operator, this is automatically satisfied if you have this, but it's not true for infinite dimensional operator. Okay, and so for example, one example, so I'll let you think about that, or maybe in the next, yeah, let me just finish on this side. And just another definition. So here, if you take, so we define the inner product. Now what is called the outer product is this object, and this is an operator, okay? Be careful. When you do calculation, you have to keep that in mind. So this has some important property for Hermitian operator. So the first one tells you that if A is Hermitian, then all its eigenvalues are going to be real. And this is going to be important because when you do a measurement of an operator, then we're going to say that the outcome is going to be one eigenvalue of this operator. So if we take A Hermitian, this is a good property because then we know that the outcome will be real. Okay? So you're going to prove this in the tutorial this afternoon. And then also the second property tells you that if you have distinct eigenvalues, then Hermitian operator must be the eigenvector must be orthogonal, and this is going to be important because usually the basis you're going to choose to represent some of the operator or your vectors are going to be the eigenvector of a given operator. So for example, well, the position is not a good example because it's infinite, but even with position. So then this means that you want to have orthogonal to find an orthonormal basis, okay? So yeah, now so be careful with infinite dimensional vector space. So I'm going to mention that now, and then in practice, we're going to use infinite dimensional vector spaces all the time and don't care so much about it, but I just want to mention this to you, that at least you're aware of it, because this means that, of course, we can do calculation and we can do everything you want, but then if, for example, in your research at some point you're working with infinite dimensional vector spaces, you can do whatever you want as a physicist, but then at the end, you will have to be a bit like a mathematician and check some of these details to make sure that this is consistent. Okay, so yeah, so we have a distinction between Hermitian and self-adjoint. And so I'll let you think about it. An example, for example, of Hermitian but not self-adjoint operator would be if you consider this operator. So yeah, I'm not going to put the define on the space of square integrable function on a finite interval. Okay, so I'll let you think about this example. So this one is Hermitian, but not self-adjoint. Okay, and you can try to figure out why the domain of P and of this operator and the domain of the adjoint are not the same. Okay. So I'll let you think about. And what is important here is that this is finite interval. Okay, so another thing you need to keep in mind is that if you have a finite dimensional Hermitian operator, then they will have a complete set of eigenvectors. So this means that you can really find a basis that spans your vector space. But in the case of an infinite dimensional vector space, it's not always true. Okay. Okay, so something that we are always going to use, as I said, usually, so we're going to work with abstract vector and abstract operators, but at some point we want to represent them. So this representation means the choice of a basis. Okay, and usually the basis you're going to choose is going to be the eigenvector of a given operator, or you want to decompose. And so what is really important, we're always going to decompose, in fact, our operator. So, and this is using the spectral decomposition. So if you have a self-adjoint operator with a set of eigenvalues which are discrete, then you can, it's very easy to find the spectral decomposition, where here PL are a set of mutually orthogonal projection operator satisfying this. And you're going to work a bit on that in the tutorial this afternoon to show that indeed it's very easy to find specific orthogonal projection once you choose adequate basis. Okay, but the issue is that we're going to, in the next few lectures, we're going to look at canonical quantization. Okay, and so what is canonical quantization? Canonical quantization means the starting point is going to be Hamiltonian formulation of classical mechanics. Okay, so this is going to be the starting point. So what is the Hamiltonian formulation of classical mechanics? This means that you work in a phase space with P and Q. Okay, and the idea is you want to quantize that. So this means that P and Q now are going to become operators, but of course these are infinite dimensional operators. They are unbounded operators. Okay, their eigenvalues are going to be continuous, and this is going to mean that the eigenvector of X and P are not going to be element of the Hilbert space if your Hilbert space is a space of square integrable function. Okay, so how do we deal with that? In practice, we're going to do calculations. So there are different ways to deal with that. The first way is to use Dirac's approach, where the mathematical framework of Hilbert space is extended to include now a broader set of states. So this means that in practice, we're going to consider that all these inner products are well defined, even if here we have a delta function that are distribution. Okay, and so this means that for this different operator, we're going to use this general spectral decomposition, where here this is a continuous parameter now. Okay, so this is really the Dirac's approach, where in fact we are not really working anymore in a Hilbert space, but in an extended framework. But in practice, yeah, so this is just to make sure that you know about that. But in practice, we are going to work with that all the time, okay? And another, just to finish, because my time is up, I just want to mention another way to generalize, to work with infinite dimensional Hilbert space. It's the von Neumann approach, okay? And the idea of von Neumann is here to keep really the notion of Hilbert space, and instead of what is going to be generalized now is the notion of observable. And instead of observable, like Hermitian operator, you're going to work with what is called POVM, okay, so projector valued measure. And then the spectral decomposition take this, this form, okay? And I'm not going to add anything on that. And in practice, for the first half of the course, we're not going to work with that, but I just wanted to mention it. But you're going to come back on that maybe with Aggie in the second half of the lecture. Okay. Yeah, so then this was just to give you, again, the definition of Hilbert space, but we're going to come back on that. It's just an inner product space. So this means that we have an inner product on a linear vector space that satisfies, in addition, that the condition of being complete in the norm. So I'm going to come back on this technical definition later on. And again, in practice, we won't care, but I just want to mention that now you have to be careful for infinite dimensional Hilbert space and or unbounded operators, meaning that the operator of a continuous spectrum without, which is unbounded, then you have these two different ways of dealing with that, okay? Okay, any questions? Okay, so I see you this afternoon for the tutorial at 2. And then tomorrow we start with canonical quantization. It's going to be quite quick, quite fast, because then I want to start path integral quite soon, because I have many things to say and it's quite technical. Okay? Thanks.